Welcome to Remote Calculus class. Today we're going to focus on an introduction to implicit differentiation. What is implicit differentiation? Well, differentiation is finding the instantaneous slope or rate of change, and we do it implicitly if our formula has the variables blended together on one side of the equal sign, or maybe even on both sides of the equal sign, but the formula is not solved explicitly for a specific variable. Here we have an example about wind chill. X is temperature in Celsius, Y is wind speed in kilometers per hour. And notice that X and Y are blended together in the formula. If we wanted the rate of change of wind speed per change in temperature, we would have to find it implicitly. By the way, all of the graphs and work in this video will be posted at the end of the video if you wanted to pause on and zoom in more on the details. We also could have an example like this cardioid, where it's not a function, but it certainly is a curve that might be studied. And at every single point, there's a slope. If we wanted to find those slopes, we would have to do so implicitly because X and Y are blended in the formula. We've got a nice example here about power equaling current squared times resistance. X is current in amperes and Y is resistance in ohms. And if we wanted to know the slope at any point, we could do so implicitly. This is actually an example where it would be really easy to solve explicitly for Y, but our topic is implicit differentiation, so we're going to leave the formula as it is, and we will find the derivative implicitly. So our formula is 0.6, because for that example, we're leaving the power at 0.6 watts, and it's equal to X squared times Y. X and Y affect each other. As you change one, the other one has to change to keep the left side equal to 0.6. But we're going to pick Y to be the dependent variable. So Y is a function of X. I'm going to replace Y with f of X to remind us of that. So now we're ready to take the derivative. On the left side, we have a constant, 0.6, so the derivative is 0 because the derivative of any constant is 0. And on the right side, we have a product, so we're going to have to do the product rule. Remember, the product rule says that you leave one function alone, and then you multiply by the other derivative, and then you do the reverse. The function you left alone, you take its derivative and then multiply by the function whose derivative you took, you leave alone. So first times derivative of the second plus the second times derivative of the first. My first function here is x squared, so I'm going to leave it alone. It gets multiplied by the derivative of the second function, so it's going to get multiplied by f prime, and then we'll add the derivative of x squared is 2x, and then we'll leave f alone and not take its derivative. So there's my product rule. Organizing it a little bit better, we have 0 equals x squared times f prime of x plus 2x times f of x. I'm trying to solve for the derivative, so I'm trying to solve for f prime. This term doesn't have f prime in it, so I will move it over to the other side. So we have negative 2x times f of x is equal to x squared times f prime of x. At this point, I think I might replace f of x with y, because it'll look a little bit cleaner. And notice if I divide both sides by x squared, I get what I'm looking for. I get f prime all by itself. So I have found the derivative implicitly. But cleaning it up, I will divide the x's in the numerator and one of the x's in the denominator. And so I get negative 2 times y over x, and that equals my derivative. So what this means is that at any point, I plug in the coordinates of that point, and that will give me the slope at that point. So we were interested in the point where amps were 0.1 and the resistance was 60. So at that point, if I plug in the 60 for the ohms and I plug in the 0.1 for the amps, I get negative 120 over 0.1 or negative 1200. And remember, we always want to put the units. So the units are ohms per amps. So at this point, as the amps increase by 1, the ohms had to decrease by 1200. Or you could also more simply say, if the amps increased by 0.01 100th, the resistance had to decrease by 12. So that was a nice beginning example of implicit differentiation. There will also be videos about the cardioid and the wind chill example. And again, at the end of this video, all of these graphs and the work are posted so you could focus on them. Have a good rest of your day.